We're recording now. Today is the second last class, and we are pretty much done with the content that I want to cover in the course. And today I thought I will kind of take you through various, an assorted set of ideas and applications that can be built on top of the various Lego blocks that we have learned in class. Okay, so in that sense, this is kind of, if you look at the course calendar for today, there's a whole bunch of things I've put in over there. Of course, these are, and there are related papers to each of them. So we of course cannot go and dive deep and understand all the details. But my goal was, thus far in the course, you've seen various building blocks and you've seen some way of applying those building blocks, right? Like Lego blocks. And today's goal is to give you a rapid fire of various structures that can be built using those similar or same Lego blocks that we've looked at in class. Okay. And of course, it's going to be a rapid fire because, as you know, in the past, we've spent a full class and often 1 hour, 30 minutes, 40 minutes. And in that same time, I'm going to cover maybe 8. So everything is going to be very kind of magazine level, right? You at a high level. But I want to give you the idea of what you can do or what other people have been doing with these kind of Lego blocks in mobile computing and applications. Okay, great. So let's get started. Any questions thus far?
Is there a pre-notes or no for this one?
No pre-notes today because I have to kind of write as I'm talking about. And if there's something that you feel interested in, we can talk about a little bit more. If there's something that's then we'll move on. Okay. So this is so fast that there's no pre-notes that we have for today. Great. Let's get started. And I'll follow this kind of flow over here. First project we'll talk about is a project called Insight that actually we did in our labs maybe 7 years, 6, 7, 8 years ago. Okay. And let me tell you the idea. So a lot of companies such as, let's say, Walmart, Target, Home Depot, right? These kind of superstores were trying to do localization. Okay. And localization was hard. You know, it's still very hard because you can do Wi-Fi, you can do Bluetooth, but all of that is hard. So one of the things that came up at that point was, hey, you have these stores, but there are a whole bunch of cameras that are installed on the store anyway. Right? These are the surveillance cameras. And if the surveillance camera is looking at some part of the store and there is a person walking along some aisle, going down some aisle, the camera can exactly, precisely locate the user on that aisle. Okay. And Walmart's goal was, hey, if I can precisely locate, if the person stops at the toothpaste shelf, Walmart wants to say, hey, there's a discount or an offer on toothpaste going on. Or, hey, did you know that this toothpaste has been, is very effective for the various things? Or if the person is standing in front of spinach, Walmart says, oh, there is a spinach recall because there is Ebola or something else going on. Not Ebola. What is that? E. coli, sorry. There's E. coli that's spreading on the spinach. You might want to be careful about the spinach, right? So many of these companies were saying, why can't we use the camera? Because that solves our localization problem completely. You're with me, right? Now, the question then became, the person has a phone over here, and now somehow the company, Walmart, needs to communicate that information that, oh, there is E. coli in the spinach, or, oh, there is a discount for the toothpaste. That information needs to go to the phone. Agreed? Right? But look, if you think of the Wi-Fi system for Walmart, maybe the Wi-Fi system has all the phones associated to it. But you do not know for this particular person what is that phone's address. Does that make sense? Right? Because if you think of the Wi-Fi device over here has 10 different addresses. Number 1 is address 1. Number 2 is some MAC address 2, so on. It has 10 different phones with different addresses. So now the question is, how do you know that address number 2 corresponds to this person? You have no clue. Moreover, Walmart also said, look, I do not want any privacy issues. Meaning, if somehow I figure out that address 2 indeed corresponds to this person, then I can start tracking what this person is buying or what this address is buying, right? Because I can look through the camera, I will know that address 2, maybe I don't know that's Alice, but I know address number 2 bought toothpaste, bought milk, bought potato chips, bought junk food, right? And later, if I somehow figure out who's address number 2, I have completely broken anonymity, right? It's a big privacy breach, right? So Walmart also said, or all these companies were saying, we want to be very careful about privacy. We do not want to use this address at all, if possible. Okay. So what do I want to do then? I want to somehow communicate to this user without using any addresses. That seems like a weird, undoable thing. Okay. So here is the core idea that came up at that point. Okay. Here, the idea is as follows. Let's say Alice, this person is Alice. Alice is walking down some aisle and Alice's phone has her IMU on. Okay. So the IMU measures walking, maybe stopping, maybe walking again, maybe turning, again walking, turning, stopping, right? This is what IMU is measuring. Make sense? Let's say there is another user, John. The first one is Alice, and the next one is Bob, let's say. Bob is also walking around the store, also has an IMU. And Bob is walking down the aisles, takes a turn, walks again, walking another aisle, takes a turn, walks. So every Alice, Bob, John, Susan, they have their trajectories of walking. And the IMU is recording that. You agree? Very good. So here's the idea. The idea is, what if the camera looks at this person, doesn't know it's Alice, but visually can see how Alice is walking and what trajectory Alice is walking? Make sense? So if the camera sees Alice walking, from the camera video, can it extract the motion pattern of Alice? Right? So if you look at the camera buffers, if you look at, the camera's recording buffer by buffer or screen by screen, you should be able to see Alice taking the first step, then in the next one, Alice taking the second step, then in the next one, Alice taking the third step, and so on. You would be able to see Alice bouncing. You should be able to see Alice turning. So the point is, can we design an algorithm which takes Alice's camera data and outputs Alice's camera/visual data outputs Alice's expected IMU data. Does that make sense? By looking at a person's video, I should be able to say exactly what that person's, how that person's pocket is moving, right? Imagine in the video, I tag the pocket of the person and then I track those pixels, right? And assuming that the phone is in the pocket, the phone's IMU motion and the camera's view of the phone's motion should be pretty identical, pretty same, right? So once you have this expected IMU data, then what the camera does, or the idea is, the camera sends a wireless broadcast message, but it creates this message whose address, this is the message. The message says 10% discount on toothpaste. But who does the message go to? The message goes to an address which is this value. Does that make sense? So now the message is broadcast over Wi-Fi. So that signal comes to everyone's phone. Okay. So Alice's phone, Bob's phone, this is Alice's phone, and this is Bob's phone. This message comes to all these phones, right? And the message has this address, which is some IMU data that has been computed from the camera. Now, Alice also has her own IMU data, and Bob has his own IMU data like that. Tell me what happens now. What am I going to say next? Anyone? This camera wanted to send this message to Alice, right? Because Alice is standing in front of the toothpaste store, and that's why this camera wants to give this 10% discount on toothpaste to Alice, but not to Bob, because Bob is standing in front of the milk shelf, right? So now, once this message comes to both Alice and Bob, what Alice does is it takes the address of this message and compares to its own IMU. If these two match, then Alice says, this message is actually for me. Bob also does the same thing. This signal and this signal does not match. Bob says, this message is not for me. Okay. Alice accepts the message and now looks into the data part of the message and sees, there is a 10% discount for toothpaste. So going back, what have you done? The camera looked at Alice's motion, from the visual data, created the expected IMU data, and used that IMU data as the address to communicate. Now let's look at what is the advantage. 1, localization completely solved, because the camera can position Alice to the granularity of a pixel. So localization completely solved. Why is privacy solved? Because the camera has no idea whatsoever who this person is or any information about the phone, right? Because the phone did not give the camera what my address is the camera has no information about the phone's MAC address, IP address, blah, blah, blah. Because the camera is just broadcasting. Right? In fact, if you think about it, if the phone had a microphone which is on, the camera could broadcast acoustic beacons, maybe using backdoor. You remember backdoor, right? We are sending inaudible communication. So it could send acoustic beacons, which has no addresses. There's no acoustic addressing, right? It's only just acoustic signals being sent. The camera could send the acoustic signal. I mean, some speaker inside the camera could send the inaudible acoustic signal. And if this microphone gets that acoustic signal, the microphone can get that data and still compare with the IMU data for Alice. And if Alice is worried for any reason, Alice can just turn off her phone. No privacy issue at all, because there's no information about Alice that the camera gets to know, except for the fact that some blob or some person is walking around in the store, which is getting recorded anyway by surveillance cameras. Okay. So what did we do in looking at this from another level is we have created a temporary identifier for a user that can be used for communication. Guys, does that make sense? At home, I want you to think of potential other applications of this. Right? For instance, can you think of an application where now Alice wants to communicate back, maybe not in the context of a store, but in some other application where the person who has the IMU wants to communicate something back. Or any other application that comes to mind where you have the visual information and this motion information, two different people, two different entities are sensing two different modalities, but they can do matchmaking by comparing these modalities. Okay, here is, again, this is not easy, but here is one more application that other people came up with. People said, suppose someone does not want, in public places, people take pictures, right? And suppose I do not want other people to take my picture, even if it is not maliciously, right? If someone is taking a picture in front of Eiffel Tower and I happen to be in front of Eiffel Tower, I don't want my picture to be in their pictures, right? Today, you don't have a way of doing anything about that, right? If someone takes a picture and you happen to be in that picture, you just cannot do anything, right? So then one thought was, if someone's taking, this is a camera, let's say, if someone's taking a picture and I happen to be, and let's say Alice happens to be in this picture, Alice is walking in the background and Alice happens to be in the picture. Can Alice's phone broadcast an IMU data? Alice's phone broadcasts to everyone the following information, which is, this is my IMU data, and if you see this data, if you see this motion, delete me. Does that make sense? Now, of course, while taking this picture, the assumption is you're holding the camera maybe for a few seconds. It's not like you're taking the camera, taking the picture and coming down, right? You're holding it for a few seconds. And while you're holding it for a few seconds, the camera is on. So let's say every time you take a picture, your camera can potentially take a video of maybe 3-4 seconds. Make sense? Because your screen has to be on for a few seconds, right? So within that time, let's say 3 to 5 seconds, you always record your screen buffer. And from that, you compute the motions of all the people that are in your viewfinder. Make sense? And now when you receive this message, maybe over Bluetooth, then you say, among all the people that I observed in my viewfinder, there is this one person who wants privacy. That person has sent us her motion signature, and I see that motion signature in my camera data. Therefore, I know that person is this person in my camera view. I will go and Photoshop her out of my picture. Right? You're enabling communication between complete strangers without exchange of any information. Right? Another idea was, and that goes back to the similar kind of Walmart idea, is a traffic light, when it turns red, it sees that a car crosses the white line, even though it has turned red. It can give the ticket immediately or give a warning immediately, right? Because the camera can now say, I know your motion from my camera. The traffic light can say, I have a camera, I know your motion. And if you are recording your own motion, here is the message for you. Right? In fact, at some point for UI/UC, we thought bikes were getting stolen. And we were thinking, if the surveillance camera can tell the person who's stealing the bike that, hey, I see you, I can see that you're stealing the bike. I mean, of course, the assumption is that the thief has to have this IMU active in their phone. But imagine tomorrow, Android turns on this capability that the IMU data is always being recorded. So I'm going to constantly record my IMU and do this matching. Then a surveillance camera on the bike stand can tell a random stranger, a random thief, that I see you stealing the bike. So please don't. You are on camera. Right? And imagine the scenario where the person is stealing and the phone buzzes and that message pops up that the camera is looking at me stealing the bike. Right? So, and of course, if it's the legitimate owner of the bike, then the legitimate owner need not worry, because hey, so what if the camera sees me? I am the legitimate owner, right? You just take your bike and move on. So I thought this was interesting, where you know all the Lego blocks, but you can still put the Lego blocks together in a way that opens up something that I feel could be actually interesting. And maybe there are many other applications possible. Make sense? Questions? Okay. Next. That's all we'll talk about. So ask me questions if you have any. Good. I'm assuming no questions. Anthony, did you have a question? I was not sure if you wanted to ask something.
Sure. I was just wondering if you could briefly just talk about, like quickly, just how exactly that comparison happens between the IMU and kind of like the message that's sent with the address IMU data and the Alice's IMU data.
Right.
Yeah.
So you tell me if, so this algorithm is the extract motion from video data. Right? This is the algorithm that you need to develop, right? From the video data.
Right.
So so that is not hard, right? Because you take a video or bunch of pictures, and you know that this person is walking, and you say, suppose you know that the person is, let's say, the phone is in the pocket, or maybe even the phone is in the hand. Then you take this particular pixel of the hand, and across all the pictures, you track how that pixel is moving. That is possible, right? So then you get a time domain signal where that's the motion of the pixel across time. Right? This is time. Right? But IMU data is acceleration. So you say, I'm going to take a D2, let's say this is PT. I'm going to do a D2 dt square of PT. Right? And that should give me acceleration of PT, of pixel P. Right? This is also a signal. This is the acceleration signal, right? Now this is what I send, and the IMU might have recorded also the acceleration of the wrist, right? Which would look like maybe the noise of the IMU would pollute that signal. And now it's a question of comparing these two signals. You figure out what metric you want for comparison. Right? I mean, you can just do correlation if you want.
Yeah, that's kind of what I was thinking.
Exactly.
Yeah.
I mean, that would be a starting point.
Yeah. Yeah. Thank you.
Sure. Right.
Everybody else.
Yeah, go ahead, Adil.
So I was wondering how generalizable this solution was. You say that localization is completely solved, right? I'm guessing the camera is like a form of like dead reckoning here, right?
Why? Because of occlusions, you mean?
Yeah.
But you know, surveillance cameras typically have full coverage.
Yeah, I guess so.
If there are blind spots, then you need to do some dead reckoning. True. I agree.
Okay.
You see, Adil, right? Your point is valid. I mean, people still steal things from superstores by finding out blind spots of the surveillance camera. Right? So yes, if there are blind spots, you can do it. It's an issue. But maybe the camera can say, when there are blind spots, I'm not going to use that portion of the motion as the signature. I'm only going to use certain portions that are obviously visible to me.
Okay.
Adil, does that make sense?
Yeah, it's just like when I think about like generalizability, I'm talking about like if you're thinking about like a Costco, right? There's so many cameras, right? I mean, I guess a company like Costco can afford it, right? But it seems like how involved you have to get in like your algorithm to have every camera up to speed at the same time, right? Like with everything. It just seems like a lot of resources have to go into that, right?
No, Adil, I think if you think of Amazon Go, right? This shop where Amazon, you don't have to check out. You just pick your things into your shopping cart and you just walk out, right? That has camera to the granularity. They know which object you are picking from the shelf, right? So my point is, occlusions is a problem, but it's not a big deal because let's say there is an occlusion here, there's an occlusion here, there's an occlusion here. These are different aisles. First of all, typically cameras are on the ceiling, right? So you're going to see the top view of, so your camera's footprint would be like that.
Sure.
Right? So there'll be another camera which will be like that. There's another camera which is like that.
Yeah.
Right? So it is a very much of a solved problem where if a person walks from this camera's footprint to that camera's footprint, this camera C1 and this camera C2 can easily re-identify that person. This is a solved problem. Right? I mean, from the color of the clothing, from the time when the camera, when the person was at the edge of the camera view, from the gait motion, there are enough information to say whatever person I saw over here, or rather whatever person I saw at this boundary is the same person that's over here. That's very easy. And that is already solved because surveillance cameras already do that, right? So then if you have top view cameras like that, then the occlusion is not that big a problem. And even if occlusion is a problem, you'll say, I'm not, suppose this is the region where people get occluded. Then you're going to say, look, I'm not going to use the motion signature for that region. I'm going to use the motion signature for this part, for this part, for this part, and so on.
How customizable does the solution have to be for like different stores? I understand like in your example, you use Amazon Go. I'm guessing like what makes Amazon Go so easy, I guess, or like really easy to solve is like these these stalls are probably not the height of the entire building, right? They're probably short enough that the camera can still see everything that's going on, right? How does this assumption have to hold for like other stores too, where like there's not much occlusion occurring because of the items that are present in the store or like the objects?
No, I mean, I'm thinking that if you think of a ceiling camera, there is hardly any occlusion because all you want to see is the motion of the user.
Okay.
Right? That's all you need to see. That's number one. Number two is, if you look at, you tell me this, okay? If two different people are moving in the same way on two sides of the store, then is there a problem?
No.
Why not?
If they're moving in two different parts of the store, then you have different devices tracking them differently, right? Like it's not
No,
like
let's say the camera can see the whole thing.
okay.
Now, let's say two people are walking identically in the IMU space.
And we're not using camera?
We are using camera. This red circle is the camera's view. And the camera wants to give a coupon to this person because this is the toothpaste aisle. Is this a problem? This is a problem, right? Because the motion signature that you're going to create from the video is not going to differentiate these two guys.
Yeah.
Right? But then observe that two people walking identically for long periods of time, that probability decreases very, very fast. So if two people are walking in a similar manner, the camera needs to wait for a longer duration to create the signature. Right? So, right? You see that, right? This person walks like this. And this person also walks like this, identical. But maybe at some point, this person takes a left turn and this person takes a U-turn. So if the camera starts building the signature from this location, the two are identical until this point. But once they take the turn, they have been disambiguated. Right?
Okay.
If you wait long enough, you can always create a unique signature.
I guess my misunderstanding came from how the camera is being used. I thought you were tracking location with the camera, not
tracking location of what?
With the camera.
Yeah, you are, right? Because you are saying that when the camera looks at this floor plan looks at the floor of Walmart, the camera knows that this is where toothpaste is, this is where milk is, this is where medicines are, or this is where nuts are, right? So if the camera sees a person over here, the camera knows exactly where the person is standing on the floor of the store, right? And therefore the camera knows, because it knows that there are toothpastes on the shelf, the camera knows that the person is looking at toothpaste.
Okay, so so we're using the camera for location.
Correct.
My understanding just now when you said that, like the I cannot speak today.
Disambiguate, yeah.
Yeah. The disambiguation happens from the difference in motion, right?
Correct.
Not from the difference in location. So
correct. Absolutely right. Exactly. So if these are the two motions, you cannot disambiguate because they are identical, let's say. But once you change, once the person comes this way and this person goes that way, that's when you disambiguate.
Now, can you tell me why not just so this technique seems really cool, but why not just use the camera? Well, I guess you can't really identify people just from the camera.
Correct. You cannot send that information to the person. You want that you want this comparison over here. You want this comparison because you want to send that message to that person's phone. Right? And the other good property of this is you can download one app that will work with all stores. Right? Because all that app is doing is recording your IMU data, and whenever a wireless packet comes, it just compares with the address of that wireless packet. That's all that app is doing. That app need not be specific to each store, that, oh, you go to Walgreens, you need an app. You go to Home Depot, you need a different app. You don't need to do that.
Okay.
Great. Okay.
I have one final question.
Sure. Go ahead, Alex.
I'm just wondering how you would deal with like different orientations of the phone when you don't like know that information. Because if someone put their phone in a purse and you have no idea which way it's facing, then how you generalize that?
It's a very good question. Okay. So this is why, I did not say anything about the gyroscope, first of all. Okay. The short answer to that question is, you want to create this motion signature or this motion signal independent of the phone's orientation. Right? For example, if you know that the pixel is moving in this way, whatever the orientation of the phone, the acceleration should still be the same. Guys, I hope this is fundamentally clear to you. Suppose my phone is moving like this, right? If my phone is oriented like this and moving like this, versus my phone is oriented like this and moving like this, if I take x square plus y square plus z square, or rather acceleration x square plus acceleration y square plus acceleration z square, square root, that value is not going to change based on the orientation, because that's my phone's net acceleration. Right? AX, AY, AZ might be different, but the length of that vector AX, AY, AZ is going to be fixed. Right? So you want to create the signature that is orientation agnostic. And it's possible. Right? So all the energy related norms, energy related signals are all independent of orientation. Right? When the user takes a turn and you see that it's a 90-degree turn, you can say that your phone took a 90-degree turn at time t3. Regardless of what the phone's orientation is, let's say the phone's orientation is this. If the phone took a 90-degree turn, right, the phone was walking like this and then took a 90-degree turn, your gyroscope is going to register that 90-degree turn. Right? Doesn't matter which axis registered how much. If you do gx square plus gy square plus gz square square root, you're going to get 90 degrees. Okay? But that's a good question. This is why it's a paper where you have to figure out these things very carefully in order to design those two signals and then match them. Good question. Okay, great. Next, if we do not finish today, we will continue the last class. Okay. So next we'll talk about something interesting. Let's talk about white track. Completely different, okay? This is a completely different project. So we are just jumping around all over the place. Okay? So white track says, I have a room and there's a person who's walking around and I want to localize the person in that room. But I don't want the person to carry any device. Okay, so what am I going to do? I will put some wireless device which will send out signals. The signals will reflect on all different environments, walls, ceiling, so forth, furniture, table, chairs, and will also reflect from the human. Okay. I am going to cancel out all reflections, all background reflections, and only get reflections from the moving human. Right? Why is this possible? Here is the broad idea. The assumption is only the human is moving and everything is static. Okay. So now when I send a signal from one transmitter antenna and I receive the signal, okay, let's think of it this way. Let's say this is one antenna, this is another antenna, and this is the environment. There are tables, chairs, couches, TVs. The signal that I send out comes to my receive antenna after multiple reflections, all kinds of things. But whatever those reflections are, I can say that if I sent a signal X, the received signal is some HX, where H is the channel. You know this now, right? But this H would remain static if everything else is static. You agree? So what this paper or what this project does is the following. It says, I'll have 3 antennas. When I transmit from this antenna and the signal comes back, let's call that H1X. When I transmit from this antenna and the signal comes back, again, I'm showing only one reflected signal. Actually, there are many echoes. Okay? But all of that is captured in H1. So similarly, all of this is captured in H2X. Okay. So this project says, I was sending X here, I was sending X here. What if instead of this X, I send a signal which is H2 inverse H1 minus. Right? This is what is X. Let me write that. Instead of X, I will send, instead of X, I send new X dash equals minus H1 H2 inverse. This is the signal. Now, when this signal arrives back over here, and this signal arrives back over here, what should this antenna receive? Can someone tell me? This antenna receives Someone tell me. H1x plus what? Plus H2 of minus H1 H2 inverse. Sorry, there's an X over here. Agreed? What is this signal? Remember, convolution is commutative. So what do you receive?
It should just be 0, right?
0. Make sense? Now, suppose some user is moving, user is walking, right? Look, this part is 0 because the environment is static. But if the environment is static, but only the user is moving, when user moves, received signal is not equal to 0 anymore, right? And the only reason it's not equal to 0 is because the user is moving, right? So now you see, right? I have a signal that's changing because the user is moving. Haha, can I start saying things about the user? By the way, guys, where have you seen this? Where have you seen channels like this?
Is it with noise canceling?
Noise cancellation. Right? See how you can use those Lego blocks in all kinds of interesting ways. Okay. So now you have to, of course, it becomes more interesting and sophisticated, but the core idea is whatever residue you are going to see is only due to the user moving, and that gives you nice opportunities. Let's watch a video. Sorry. Let's watch the video here.
This video shows Wi-Fi, a device that can track.
Can you hear that? Is it too loud? Is it okay?
It's fine.
A little bit too loud. Okay.
Human motion behind walls and.
Okay, let's start from the beginning, okay?
This video shows Wi-Fi, a device that can track human motion behind walls and in closed rooms. Wi-Fi is behind the wall as indicated by the red arrow. The blue window at the bottom shows the output of Wi-Fi. The room is initially empty. This is why the signal is 0. A person enters the room. As he moves away, the device shows a negative signal. When he moves toward the device, it shows a positive signal. When he stops, it outputs only the 0 line, meaning there is no motion. Even when he performs a minor movement like now, Wi-Fi registers it.
Okay. So this is kind of a first take on how you can use
behind walls and enclosed.
How you can use just wireless signals to do localization. I mean, this is not yet localization, but you can see how things can get translated. Okay.
I had a question.
Yes, go ahead.
That second term, the H2, negative H1, is that an eigen decomposition? I'm not too sure though.
No, that's not eigen. Why?
Well, it seems like you're bringing into the H2 basis, then you're multiplying by well, the eigenvalues, I guess, h1, and then you're taking it out of the h2 basis?
This is a vector.
Oh, okay.
This is a vector.
Oh, right. They're
This
convolutional.
H1 is a, you remember, right? Multi-tap channel, K-tap channel.
Yeah.
This would
Okay.
be just K-tap channel.
Okay. Yeah.
Perfect. Very good. Okay. Let's switch topics. Okay, that's all we'll talk about. But if you want, you go to these links on the web page and you'll see many other pointers from there. We'll talk about another topic, another somewhat related topic, and this is a project called CAT. I forget what the full name is, what the acronym stands for. But the idea is the following. You have a TV and a person sits on the couch and uses a remote. Today we use a remote to control the TV. Okay. What this paper says is, I want to track the motion of the remote, because based on that motion, it can become a mouse. And the way I want to do it is that I want to put a speaker which is sending a signal. Here I want to put a speaker which is also sending a signal. No, sorry, my bad. It says that there is a speaker over here that is sending a signal, a speaker, and there are microphones on the TV that will receive the signals. No. Wait. Okay, I'm forgetting the exact detail, but I will tell you what the technique is, and maybe that will be useful. Okay. Okay. So imagine there is a speaker which is sending out sound, and there is a microphone, and there is an object in your hand. Okay. And the speaker signals that reflect off the object and goes to the microphone. From that received signal at the microphone, you want to understand how this object is moving. Okay, so this is similar to this previous problem, right? Except that now it is with acoustic signals. The signal is shining. This is like radar. The signal is shining. The signal reflects off an object, and you want to track the object. Okay. By the way, guys, this goes a long way back where, for example, let's say you have a submarine and the submarine wants to do sonar, right? It has a speaker. It sends a sound signal underwater, and there's a torpedo that's coming towards this submarine. And by looking at the reflection of the torpedo's body, the submarine can figure out where the object is. Okay. So let's talk about what the technical challenge over here is. The technical challenge is when you transmit this signal, and when the signal comes back, let's say the signal is coming back at your microphone. this signal that you're transmitting also comes directly to your microphone. Do you agree? So now tell me, between this signal and this signal, which one is more powerful?
The direct signal.
The direct signal is far more powerful. Why?
Because some of the energy is absorbed off the reflections for the other signals. So
because say that again, Anthony.
Some of that energy is absorbed when it becomes reflected off of, say, other obstacles like a couch or a chair.
That's number one. Give me a second reason.
It has to travel a lot farther.
It has to travel a lot farther, right? So the energy is dissipating, right? So by the time the energy reflects off this wall, that amount of energy is a much smaller fraction of the whole energy that the speaker has transmitted. Agreed? So this is a much stronger signal than this. So then if you want to figure out this signal, that is a problem that looks like the following. You are receiving a signal like this, but this signal is actually made out of some signal like that, plus some signal like this. Sorry, actually I should correct myself here. The blue signal is much closer to the black signal, but there's a red signal also, right? Such that red plus blue equals black signal, right? But observe that you do not know the red and blue signals. The only thing that you observe, sorry, the only thing that you observe is the black signal. And now I ask you, can you pull out the red signal? Because the black signal is made up of red and blue. Very hard, right? One possibility is, look, you know what you're transmitting, right? So you might be able to subtract the transmitted signal. Of course, there is a channel over here, which is, let's say, H, right? So what you're receiving is some H of X. So you're receiving H of X plus some reflection of X. But because you know X, and because maybe you can characterize H, you might be able to subtract this. But if the reflection is very weak, meaning the reflection is almost close to noise, then it becomes hard. Because if you do not subtract this HX perfectly, the residual, the pollution that you have will make it difficult to pull this signal out. Does that make sense? Okay. So there is a technique called FMCW, which is frequency modulated carrier wave. Sorry, continuous wave. Okay. So what they do is an interesting idea. And this is what they want. This is the basic idea that I'm going to draw soon. All they want is they want to compute the time it took for the signal to reflect off this object and come back. It wants to know that time. Because if I know the time, I can estimate distance from this device to this reflector. You agree? If I know time, I can get distance. So this is what they do. They say, look, I'm going to take a signal, in fact, a tone, just one frequency signal. All of you know by now that if this is frequency, and if there is one frequency over here, then what is this signal, guys? If there's only F1 and minus F1, which means there's only one frequency. What would you say is the time domain version of this signal?
A cosine wave?
A sine wave. Okay, so that's one thing, right? So it's a sine wave. It's ping, right? So FMCW says, let me take a sine wave, but I will keep changing its frequency. So that signal would look like the following. I'll keep changing its frequency over time, right? So the signal will be like, I start off with a low frequency, and then I increase my frequency, then I increase my frequency, then I increase my frequency. That's what the signal will look like. Right? And then once I'm done, I'm again going to do the same thing. Okay? And I'm going to continue. Okay? Now look, when this, so this signal is this signal that's going out. Right? So now when the signal comes to you after a reflection, what you get will also be this, right? But when the signal arrives after the reflection, what is the direct signal that you are getting? So in other words, imagine any time instant. Let's say time instant t1, or let's say time instant ti. At time instant ti, okay, let me just draw this first. At time instant t1, what is the direct frequency you are going to get? Let's say this direct frequency is, let's say, almost instantaneous because it's very quick, right? Because your speaker and your receiver, your speaker and your microphone are just co-located. So at time t1, what is the frequency that you're going to get directly?
Is it the F10 frequency?
F10, right? So you get F10 directly. What is the reflected frequency you're going to get?
F5 frequency.
F5.
Yeah.
Right? So your direct frequency is F10, your reflected frequency is F5. Make sense? And now look. You know the slope of this line. Why?
Is it because you're controlling?
Because you're controlling the signal, right? So you know this theta, right? You know theta, oops. Because you are controlling the slope of that line. You are changing the frequency in this signal. You know theta, and now when these signals come into your microphone, what you do is you multiply them. Meaning the red and the blue signal over here is coming. There are ways to multiply the signals that are coming. Those are called mixers. So now when you multiply a sine F10 with a sine F5, what do you get? Okay, you basically get frequencies f10 plus f5, and you also get f10 minus f5. Okay, so what is f10 minus f5? f10 minus f5 is this value. You agree? What do you want? You want the time it takes for the signal to go and reflect back and come back. Which value is that? This is this value. Make sense? Because this is the time it took for that frequency to reflect and come back to you. Someone tell me, how do I solve for this time? Because this is what I care about. This tau is what I care about. So how do I solve for tau?
Is it kind of like tan theta is equal to the, yeah.
Okay. You know this. You know this. Haha, you solved tau. Right? So in other words, what you're doing is you're saying, look, the signal that I'm sending out and that is directly hitting me, I'm going to move it to a different frequency quickly so that the reflected signal that's coming back is not in the same frequency. Right? That's how I separate. Okay. And once you get tau, now if the object is moving, tau will constantly change, right? And now you have a sense of how the object is moving or how far the object is, or the submarine can figure out how far this torpedo is. And if the torpedo is coming towards the submarine, tau will keep decreasing. Right? And how do you see f10 plus f5, f10 minus f5? Well, at the output of your receiver where you're multiplying the incoming signals, you will see a new frequency spectrum. Your FFT will show a new frequency spectrum, which is f10 minus f5, f10 plus f5. Right? And this will show up in your frequency, and you know that you are transmitting some frequency over here that's constantly changing, and you can separate out this frequency because that is not something you're sending right now. Where have you seen this? Or this part at least? Two frequencies, when they're multiplied, it becomes plus and it becomes minus. Where have you seen this? Backdoor. Inaudible attacks, right? We were sending this high frequency signal that was getting multiplied to itself, right? We were sending F 40 kilohertz and 50 kilohertz, and it was getting multiplied by the microphone's amplifier and the diaphragm, and it was creating 50 minus 40 and 50 plus 40. Right? Look how you can use this in other applications as well. Very good. Questions? Okay, if no questions, maybe one more. Yeah. There's a project called Liquid or Liquid ID. And the goal of the project was, I have a transmitter antenna, which will send out wireless signals. I have a receiver antenna, which will receive wireless signals. And the project says, I'm going to put a bottle of liquid between these two antennas. and figure out what this liquid is. For example, is this Coke, Pepsi, green tea, vodka, tap water, mineral water, etc., etc., etc. I'm going to figure out these liquids at that granularity. Okay. How? Well, the core idea is when this liquid is not there, okay, we are going to measure how much time it takes for the signal to go from the transmit antenna to the receive antenna. Okay. How much time it takes to go from the transmit antenna to the receive antenna is not super easy, but let's say you can do that. In fact, the way this project solves the problem, it says that, okay, how do I know exactly how much time it takes to go from a transmit antenna to receive antenna? Because remember, that's our GPS problem, right? It's not easy, right? Because the clocks are not synchronized. And in this case, because the signal is again traveling at the speed of light, even if your clock is not synchronized at the nanosecond or picosecond level, you can go dramatically wrong. So it's hard. So what this paper says is that to first compute how much time it takes without a liquid, how much time it takes for the signal to go from the transmit antenna to the receive antenna, they put a wire between the transmit antenna and the receive antenna. Okay. And they say, I will send the signal, I will fork the signal and send it over the wireless path as well as the wired path. Make sense? Okay. In the wired path, the signal will arrive earlier and then it will arrive at over the wireless path. Okay. So by measuring with respect to the wire, you do not know how much time it absolutely took, but you know how much time it took or what is the difference it took over the air compared to the wire. Make sense? If you could connect a wire from the GPS satellite to your mobile phone, you could have done triangulation in this way. Sorry, trilateration in this way. But you need to connect a wire from the satellite to your phone. But because this is a small apparatus, right, imagine a cup. Imagine this cup, which has one transmit antenna on this side and another receive antenna on this side. And there's a wire underneath the cup that connects the two. And the goal of this cup is whatever liquid you pour into that cup, a smartphone app will record you drank 2 cups of Pepsi today morning and 1 cup of coffee and 1 cup of tea. Okay. So now once you put a wire, you have a reference and then you measure the air channel's distance or air channel's time relative to the wire. And then you put the liquid in. And the idea is because signals propagate at different speeds through different materials. Why? Because of refractive index, signals bend at the boundary of liquids, at the boundary of materials. Right? Refractive index. Remember, right? When there is a liquid or some object, the signal arrives like this and bends towards the perpendicular. Remember refractive index, right? So when the signal bends, the speed of the signal changes. As a result of that, this propagation delay through the liquid changes. And now, if you can precisely figure out when the signal arrived at your receive antenna, then you can figure out with respect to air, this was air, with respect to air, how much did the liquid slow down the signal? Right? In other words, you know the difference between air minus wire. you know the time difference between air minus wire. You also know the time difference between liquid minus wire. Because when you have the liquid, you're also using the wire as a reference. Now you can do this minus this, right? Which will give you tau of air minus liquid. Tau of air minus liquid is exactly how refractive indexes are defined, right? This notion of oh, this is theta and this is alpha. This theta and alpha can actually be mapped to the velocity of the signal in the air and the velocity of the signal in the liquid. It can exactly be theta and alpha have the same relationship as the velocity of the signals in the different medium. And once you have the velocity, you can translate that to tau air and translate that to tau liquid. And then you can solve for them, right? And as a result, you can figure out the refractive index. And once you know the refractive index, you know what that liquid, I mean, actually you can do a bunch of other things. You can compute the permittivity of the liquid. And once you know permittivity, you can actually compute with a reasonable good accuracy what that liquid is. Who cares about this project? Well, a lot of people care. Medical science people, well-being, mobile health people, they care about how much you're drinking, diabetes, what is your liquid consumption. So if you can create a cup which has this electronic circuitry, you can constantly measure for that person every day what that person is taking in. Other examples, airport security. Today, if you take a bottle of wine, a perfume, they chuck it in the trash. Imagine if you have this ability to actually put that bottle in some X-ray machine, and the X-ray machine says, this is not any inflammable, any dangerous liquid. This is good to go. Third application, in many places, there are problems such as people put tap water in mineral water bottles and seal them. Okay, these kind of illegal stuff happens. So it might be helpful if you have something like this kind of a device, maybe running on your phone. It might be helpful to put the water bottle on your phone and your phone says this is tap water or this is actual mineral water or distilled water. And it turns out that mineral water, distilled water, tap water, they actually have different permittivities that you can pull out from these kind of radios. Okay. Great. So, and I'll finish in 1 minute. On a final note, these kind of applications have also been used in farming. There are this project called FarmBeats from Microsoft, which has recently been very exciting in the sense that they want to do digital agriculture. They want to precisely know what a farmland, they want to sense and measure farmlands and accordingly maybe give fertilizers, give water, etc. And one of the projects they've done is where they've put a bunch of antennas underneath the soil. And their goal is to measure. Hello? Can you hear me, guys? Guys, can you hear me? It's frozen. Hello? Okay, let me record it. Their goal is to basically send.
Yeah, good.
Can you hear you, Professor?
No.
Can you hear me now?
Yep.
Yes.
Okay. I think I lost you, but But okay, we'll pick it up from next class. But I just wanted to say that this farm beats project around digital agriculture, they're putting these antenna arrays underneath the soil, and they're sending wireless signals from a drone. Okay, and the signals are coming from the drone, penetrating through the soil and coming to these antennas. And based on the moisture in the soil, the speed of the signals are varying. And if you apply beamforming kind of algorithms, you can see what is the phase difference, because if these signals are slowing down, then at different antennas, the phases would be different. And from that, you can infer what the soil moisture is. So again, it applies these phase changes, beamforming with these time of flight kind of estimations to figure out what is soil moisture. Okay, so I hope you see in this lecture, we are trying to look at all possible ways of combining these Lego blocks to create, I mean, what I would say is pretty interesting technology for the future. Okay, great. We will stop there. Any questions? 11:24. Shoot, even today I couldn't finish it.
I have a question.
Yeah.
Can you do the same thing with air moisture?
With air moisture?
Yeah.
Ooh, that's a good question. Oh, you know, that reminds me, I think it's possible, because I remember someone talking about, can you use cellular signals, cell tower signals that are being received from phones and other devices to do microclimate analysis, right? So how much of moisture is there in the air, whether there is fog, whether there is mist, is there rain, blah, blah, blah. Can you do microclimate? So can you figure out how much it rained in what parts of the farm based on signals that many phones have received when they went around that farm? So Adil, I think the answer is yes, but it's a harder problem than liquid, because moisture there's less water content in the air. But definitely certain frequencies are resonant with water, meaning when that frequency passes through water, that frequency gets heavily absorbed. So definitely, I think you can say things about air moisture. I don't have the details.
Okay. All right. Thank you.
Wonderful. Other questions?
For LiquidID,
Yeah.
Can't you cheat it using like different containers with different refractivities as well?
That is true. That is true. So you can cheat it, but what we were thinking was, one possibility is, if I can pour out the stuff from the container, put the container empty, figure out the time of flight, then pour back the liquid and put it in, then I'm fine, right? You agree? So that is one possibility, but that is still a pain for things like wine. That might be okay for, you know, baby's milk, right? Even now they actually, if you carry baby milk, they would let you go through, but they will test the milk and they will stop you and you'll get delayed. I mean, this happens all the time. Right? But for things like baby milk, maybe you can pour it into a separate container, do all of that and pour it back, right? But the other thing you're thinking was, maybe it's also possible that in anything that you want to take through security, you cannot fill it up to the top of the container. Then what you can do is you can send a signal on the top of the container, which is an empty part, and send another signal at the bottom of the container. But then someone can still cheat by designing the container with a different material on the top and a different material at the bottom. I mean, you can still cheat. Yeah. So don't have a good answer to that, but you can make it harder and harder to cheat. Or you can say you can only take it through containers that have been purchased through where the container has some marker, where the container is only sold by TSA. Right? You can try to do those kind of things. So yeah, how this turns into an exact technology for airport security, there are some loopholes, there are some gaps that need to be solved. Other questions?
Thank you.
Yep.
Professor, I just had a question.
Sure.
Again, with LiquidID, as far as you talked about the granularity, saying like knowing between, say, like tap water versus mineral water. I was just wondering, as far as if there are any kind of like, say, upper or lower bounds as far as just the granularity that you can get like with a liquid or with certain types of things, and if there's like a like mathematical theory behind or physical kind of like thing that provides that
Uh,
boundary.
Actually, this is what goes into spectroscopy,
Right.
right? So this is something that is of interest to several of us. There are mathematical theories because at the boundary of two different materials, Maxwell's equations and related equations tell you what is the behavior of these signals. Okay, so people definitely understand that. But the challenge over here is really you want to do all of these with cheap radios.
Okay.
Right? So that's where the real challenge is. If you want to think about mathematically, you know how to solve Maxwellian equations and really compute these material properties. So we are more interested in what is the limit using these narrow band, noisy, right? Low frequency, clock unsynchronized kind of devices. So it's like poor man's spectroscopy. What is the limit of that? And there are lots of people who are asking us, if I mix in sugar, can you detect? Can you detect how much sugar there is in this liquid?
Mm-hmm.
Can you detect mixtures of two liquids? Right. So a lot of people said, drugging people in bars and pubs is a major issue, right? They say, okay, given that there is alcohol in this material, if I put some drugs into it, can you say that you don't have to say this is alcohol, but can you say something has changed?
Sure.
Right. So there are, and we don't have a handle, but these are very interesting future facing topics.
Got it. So it's kind of like the advantage with, I guess, this is that, I guess, the wireless radios are cheaper than, say, the spectrometers.
Exactly. It's in your phone, right? Every time you take a drink from the bar, let's imagine that you put a phone, you figure out that this drink has not been contaminated, you drink.
Got it. Yeah, thank you.
Yep. Anyone else?
I have another question.
Yes, please, Adil.
For FarmBeats, how does it compare with like traditional conventional ways of like measuring moisture energy wise?
Oh, so conventional moisture sensing is basically you have these sensors that you can buy out of Amazon and you stick it into the soil and you put them on all parts of the farm. Okay. And someone has to manually go and read the sensor, get the reading out of the sensor, come back and then do all the analysis.
But why can't you just do like IoT networks with it, with the sensors?
Oh yeah, that's a good question. Yeah, I think, maybe, okay. So I take it back. Maybe that's not the problem. The problem
I think maybe the problem was how often you replace the energy or like the batteries for all those sensors. I don't know. But I mean, you still have antennas planted everywhere too for this way.
That's true. Actually, that's a good question, Adil. I've forgotten what is the motivation for putting antennas underneath the soil. I'll come back with the motivation to you next class. I've forgotten why they want to do that, right? But the technique is that the signal bends when going through more moist soil as opposed to less dry soil.
Yeah. Maybe it's because you don't need more parts to your device. Maybe you don't need a moisture sensor because your antenna doubles as a sensor and the communication relay.
Possible, because anyway you're putting in wireless devices underneath the soil, right, for many other purposes for digital agriculture. So you repurpose those wireless devices as a moisture sensor as well. That's true.
Yeah, probably.
Okay.
All right, thank you.
Thanks. Guys, I have to go for a talk. I have to give a talk today at a different place. So I want to finish this early. Chunkai, do you have a question?
Yeah, so actually I sent you an email 2 weeks ago regarding the thesis advisor. So
I saw that email. I will respond to you today.
Okay, that'll be great. Thank you so much.
Thanks a lot. Yeah. Okay, guys. Thank you very much. And I'll see you next class. Next class is the last class, and we'll continue with the last few. Hey, there are a couple of interesting ones. So tell your friends who are not showing up to maybe show up for the last class. There are some interesting ones that we'll talk about, and we'll kind of quickly wrap up the class, and we can chat about anything that you want to. Okay, great. By the way, I see, yes, the evaluation sheets are out for the course. Please fill up the evaluation. It is valuable to me because I figure out how to change the course, what I can do better, and so forth. And I also want to know what went well, because that I can keep doing more and more. So if you give me feedback, that will be very useful. Okay. Thanks, guys. I'll see you on Wednesday.
Thank you. Good luck with your talk.
Thanks.
Thank you.
Thanks.